There is a problem with our understanding of the universe. By all accounts, cosmology is about to go off against one of its most basic questions. How quickly is the universe expanding? Two types of estimation have been at odds with one another for more than 10 years. The rate of expansion, known as the Hubble constant, is typically found to be about 9% faster in the contemporary universe than it is predicted to be based on data from the early cosmos. Experts believe that the James Webb Space Telescope, the most sophisticated telescope ever built, would contribute to a definitive resolution of the question. Unfortunately, agreement has yet to materialize. Instead, the world's best observatory has confirmed the mistake with remarkably accurate new measurements that pose a danger to the cosmological standard model. It's currently up for debate whether the 40-year-old theory should be changed or replaced by new physics, raising the startling and fascinating potential that there is still much about the universe we don't comprehend. Come explore in depth how James Webb's most recent ultra-deep photos have confirmed that there is a serious problem with our current understanding of the universe. With a bang, the Big Bang, our universe came into being. In the blink of an eye, space, mass, and energy all became real. Then the young cosmos began to form, a rapidly expanding, churning stock of matter and antimatter particles that leaped into reality only to collide and destroy one another. The matter and antimatter inside this plasma would have devoured each other to ashes if left to their own devices. But according to physicists, a subtle imbalance prevented the cosmos from imploding too quickly by allowing more matter than antimatter to form. Gravity compressed and heated the materials inside the plasma pockets, causing baryon acoustic oscillations, sound waves that move at a speed slightly faster than light, to ripple across their surface. Meanwhile, space-time expanded because to the enormous energy density of the crammed stuff of the early cosmos, which pulled a small portion of this securely from the fry. According to the conventional theory, when the universe expanded like an expanding balloon, normal matter, which interacts with light, hardened around invisible dark matter clumps to form the first galaxies, which are linked together by a vast cosmic web. Initially, the expansion rate of the universe decreased as its material dispersed and its energy density increased. Galaxies, however, started to retreat once more at an ever-increasing rate some 5 billion years ago. Dark energy, another enigmatic and invisible material, was the cause. The most popular and straightforward explanation for dark energy is that it is an inflationary force that permeates spacetime and is a universal phenomenon, known as the cosmological constant. In his general relativity theory, Einstein gave it the moniker lambda. Dark energy gradually became the primary driver of the universe's overall expansion as general matter density decreased and dark energy density stayed constant. The maximum expansion speeds of the cosmos are included in the energy densities of normal matter, dark energy, and light. They are also essential components of the cosmological lambda cold dark matter, lambda CDM, model, which directs the universe's expansion and foretells its end. Matter experiences the big freeze, a thermal death, when it is dispersed that far. It has been demonstrated that many of the model's predictions are remarkably accurate. Nevertheless, this is where the issues arise. Cosmologists have done a great deal of searching, yet they still don't know what dark matter or dark energy are. Most people agree that the universe's current makeup is 5% normal matter, 25% cold dark matter, and 70% dark energy, stated Ofer Lahav, an astronomy professor at University College London who is involved in galaxy surveys of dark energy. The sordid truth is that we are unaware of the final two. But a much bigger obstacle to the lambda CDM model has surfaced. The Hubble tension is the difference between the apparent rates at which the cosmos appears to be expanding based on the method used by astrophysicists. The early universe is expanding far more quickly than the lambda CDM model predicts, according to methods that take this into consideration. Numerous observations have verified and tested these procedures. As an example, the team that produced the latest James Webb estimate was led by Nobel Prize-winning physicist Adam Rees, who stated that the only reason I can understand for them to differ is that the model we have between them is maybe missing something. More is needed to measure the expansion of the cosmos than just a radar gun. The primary technique used to quantify this expansion is the so-called cosmic microwave background, CMB. which is a trace of the earliest light in the cosmos that was produced just 380,000 years after the Big Bang. The Hubble constant should be seen throughout the whole sky thanks to the imprint, which was created between 2009 and 2013 by the European Space Agency's Planck satellite with an uncertainty of less than 1%. The universe appears mostly uniform in this baby picture of the cosmos, but hotter and colder regions where matter is more or less dense show where baryon acoustic oscillations caused it to clump together as the universe formed. The structure, resembling a soap bubble, expanded into the vast cosmic web, which is a web of interconnected strands where galaxies eventually arise. Cosmologists determine the amounts of dark matter and normal matter, as well as the values of the cosmological constant and dark energy, by observing these waves with the Planck spacecraft. When this was fitted to the Standard Model, the Hubble constant came out to be roughly 67 kilometers per second per megaparsec. There are 3.26 million light-years in a megaparsec. Let's think about this quantity for a second. A galaxy will retreat from us and from it at a speed of 67 kilometers per second if it is 1 megaparsec away from us. This recession increases to 1,340 kilometers per second at 20 megaparsecs, and then it increases much more sharply. A galaxy will recede from us faster than the speed of light if it is farther distant than 4,175 megaparsecs. Cepheids, dying stars with helium gas outer layers that expand and contract as they absorb and emit radiation, provide a second technique to determine this expansion rate. Occasionally, these stars shine like far-off signal lights. Astronomer Henrietta Swan-Leavitt observed in 1912 that a Cepheid's pulse would slow down with increasing brightness. This finding allowed astronomers to determine the absolute brightness of a star and, consequently, its distance. It was a seminal discovery that made Cepheids abundant standard candles for determining the large-scale structure of the universe. Through the consolidation of Cepheid sightings, astronomers are able to construct distance ladders, with each step advancing their understanding of the past. Astronomers begin by choosing neighboring Cepheids and comparing their distances determined by geometry with those based on pulsating light in order to create a distance ladder. Cepheid measurements alone are used to add the subsequent stages. Then, as the universe expands, cosmologists measure how far apart stars and supernovae are from one another and note how much of their light has been redshifted, or stretched into longer, redder wavelengths. This provides a precise value for the Hubble constant. Using this technique, Rees et al., 2019, trained the Hubble Space Telescope on one of the closest neighbors of the Milky Way. The conventional theory of cosmology holds that the cosmos was initially an inflating vacuum. It expanded because of its extremely high energy density and strong gravity. It spread more quickly, and with more repulsion the more energy there was. This vacuum was chaotic, in accordance with the laws of quantum mechanics. At random points, it collapsed into the regular vacuum, creating matter and raising it to extremely high temperatures, which led to Big Bangs. Our cosmos is but one of these Big Bang bubbles within the expanding inflationary void. Remarkably, all of this may have begun with a small piece of inflationary vacuum, about the mass of a bag of sugar. The principles of physics, particularly those pertaining to quantum mechanics, conveniently permit the creation of such substance out of nothing. The next logical inquiry is, of course, where did the physics laws originate? German mathematician Emmy Noether clarified this in 1981. She realized that the principles of conservation are only the outcome of profound symmetries in reality, which are things that hold true regardless of how we choose to view them. Such symmetries have the startling characteristic of being symmetries of the vacuum, or of an entirely empty cosmos. Therefore, the move from nothing to something might not have been all that significant. It might have just been a shift from nothing to an undifferentiated something. What caused the change to occur? The fact that water condenses into ordered ice at low temperatures was brought to light by American physicist Victor Sanger. He conjectured that the world began as nothing and evolved into an undifferentiated something, since ice is more stable than nothing. Why would every galaxy have a big black hole in its center? As far as we know, almost all of the 2 trillion galaxies in our universe have a center supermassive black hole. These monsters range in size from roughly 50 billion times the mass of the Sun to the massive Sagittarius A*, which has 4.3 million solar masses. In the Milky Way's center, Yet one of cosmology's biggest unanswered mysteries is how they got there. While we are aware that a stellar black hole forms after a supernova explosion, the formation mechanism of a supermassive black hole spanning the majority of cosmic history remains unknown. A large amount of matter is concentrated in a limited volume near the center of galaxies. It is possible that massive black holes form inside a dense star cluster composed of individual stellar black holes that keep merging with one another. An indirect source of evidence for this is the combination of two: gravitational wave detection of black holes. One of the black holes was too big to be a leftover from a starburst, suggesting that it originated in a previous merger. The direct collapse of a huge gas cloud is an alternate process for the formation of a supermassive black hole. Supermassive black holes might arise as a result of merging black holes and cloud collapse. Another possibility is that massive black holes originated during the Big Bang itself. This might provide an answer to the cosmic chicken and egg question. Supermassive black holes or galaxies formed first. Maybe supermassive black holes created first and provided the seeds around which star-forming galaxies evolved, rather than galaxies developing first and then giving birth to these monsters. Even the largest supermassive black holes are not larger than the surrounding planetary group despite their immense masses, but they spread their power across billions of light-years by jets of matter traveling in opposing directions at extremely high speeds. In the innermost parts of a galaxy, these swift jets push out gas and suppress star formation. They compress gas and start star formation where they slow down in the outer regions. Actually, most stars that form appear to be controlled by strong jets from the biggest black holes, with a preference for smaller, cooler stars like our Sun. Who knows, then? We could even be able to thank Sagittarius A** for giving us our Sun, as without it, you most likely wouldn't be here. Either too little or none at all is emitted by dark matter for us to notice. Because we can observe its gravitational pull on observable stars and galaxies, we are aware that it exists. For example, without a quantity of invisible stuff, whose increased gravity hurried things up, the Milky Way could never have drawn in enough matter to produce its stars in the 13.8 billion years since the Big Bang. The Planck spacecraft of the European Space Agency discovered that whereas regular baryonic matter makes up 4.5% of the universe's mass energy, dark matter accounts for 26.8% of it. Thus, it is around 6 times more massive than the stars and galaxies that are visible. Weakly interacting massive particles, or WIMPs, have been the preferred candidates for dark matter particles for many years. These particles meet the necessary conditions, however operations at the Large Hadron Collider in Geneva, Switzerland, have not produced them. A hypothesized subatomic particle called the superlight axion is one possibility that is gaining traction. Dark matter could also be thought of as early-stage black holes that were left over after the Big Bang. Despite decades of seeking, no Earth-based experiment has mysteriously discovered any evidence of dark matter. It's feasible that our theory of gravity has to be adjusted rather than our theory of matter. Alternatively, dark matter might be a more complicated substance, similar to the conventional matter we observe around us, rather than a fluid composed of a single particle. Perhaps there are a lot of dark planets, stars, and even dark life in the universe.